These days, it's impossible to escape news about machine learning and artificial intelligence. If you would believe newspapers and journals like The Economist or McKinsey Insights, it would seem that the robot revolution is just around the corner. It's true that we have seen a number of very cool applications of machine learning in recent times, such as in autonomous vehicles and chess robots. But at a fundamental level, these algorithms are really just fitting a very complicated function, with lots of parameters to a lot of input data. Machine learning ideas have been around for decades, so why is there now such an interest? The cornerstone of the current era of machine learning, or AI, is probably the neural network, especially deep neural networks. Inputs are fed through the input layer and pass through multiple layers of hidden nodes to finally the output node. It turns out that these structures, built up from very simple components, can approach and represent basically arbitrarily complex functions. The network decides what to do with the inputs via a set of weights stored in each input node, which determines how much each input to the node contributes to its output. These weights can be optimized by comparing the output of the network and the expected outcome, and propagating the errors backwards through the network, so-called backpropagation. The continuous updating and improving of the weights of the network is what we call training of the network. Of course, this kind of visual representation is only for our own understanding. Underneath the hood, what is really happening is a lot of matrix algebra, optimized for efficiency. It turns out that these kind of calculations can be highly parallelized and therefore accelerated when they are performed on a graphical processing unit, or a GPU. The realization of GPUs as general-purpose computational units is arguably the technology that has enabled the explosion in the machine learning and AI space. Without GPUs, it is highly impractical and time-consuming to train these very deep neural networks that are used for all kinds of applications that we take for granted these days, such as image recognition. These days, we don't have to program any neural networks from scratch. You can just use a high-level library like TensorFlow or PyTorch. But what the real power in these libraries is their GPU acceleration, enabled by CUDA bindings. If you only need neural networks, you don't have to deal with this lower level stuff at all, and you can be perfectly content just knowing the higher level libraries. But what if you don't need neural networks, but you have other kinds of problems that you may want to accelerate with a GPU? How do you even know that a GPU would help for your problem? For this, we have to understand the basic differences between CPUs and GPUs. Here you see a very basic level diagram of a CPU versus a GPU. Classically, we run all our programs on CPUs, which specialize in serial execution, meaning one step after another. Modern CPUs contain multiple cores, and those can be taken advantage of in some programs with multiprocessing. The programs running on these cores in series typically run very fast because there's lots of extra cache or memory packed in close with these cores. This allows the CPU to store quite a lot of intermediate results and optimally reuse data. CPU clock cycles are also very fast, but typically a CPU contains from 2 to maybe tens of cores. By contrast, a GPU typically contains hundreds or thousands of cores that can all perform calculations independently. However, there is less space for cache, so a GPU is not well suited for complex control logic, and typically a single GPU core performs a calculation much more slowly than a CPU core. It's really through the massive parallelization that a GPU achieves its superior speed on some problems. Therefore, a GPU shines on problems that can be divided into thousands of simple little tasks that can all be executed independently and in parallel. This oftentimes involves operations on large arrays of numbers, with applications in image processing, graphics, 3D rendering, and as mentioned previously, neural networks. So if you're not dealing with neural networks, when might you care about GPU programming? Well, the most likely scenario is that you are some kind of scientist who needs to do a lot of data processing or some scientific computing. You may be familiar with Python and the scientific Python stack like NumPy and SciPy, but it takes forever to process your huge data set and you want to see what a GPU can do. Or maybe you're just a hobbyist who likes to delve a bit deeper into fundamentals. Whatever your background, you will discover that GPU programming is usually not as easy as writing a Python script, and therefore quite a niche field that is traditionally a reserved domain for the initiated. the real C and C++ programmers. I was in this very situation, and with this video, I aim to introduce some topics to bridge that gap at least a little bit. I was too stubborn to learn C++, so I looked into solutions that are available for Python, and in this video, I'll introduce you to Cupy and Numba. So how do you choose the tool you want to use for accelerating your calculations with the GPU? If you want to work with neural networks and machine learning, chances are high you just need TensorFlow or PyTorch. If you, on the other hand, want the highest level of control over the hardware, there will probably be no way around to using CUDA in C or C++. There is a Python library called Numba.cuda, which aims to bring you the full power of CUDA C in Python. However, to operate it, you basically write CUDA C code in Python strings, so you can't avoid learning the C and C++ syntax. In this video, we'll talk about two intermediate solutions, Cupy and Numba. Cupy is definitely the easiest one to work with, and if you are a scientist working with NumPy and SciPy, it's likely this will be all you need. It's very high level, pretty much on par with TensorFlow and PyTorch, but it's not specifically aimed at neural networks. Instead, it aims to behave like NumPy, but on the GPU. If you need custom algorithms, however, you can't get around to writing your own CUDA kernels. We will talk about kernels later in this video. Numba is a very cool project that has bindings to CUDA, and it allows you to write CUDA kernels in Python, so you can very closely approximate CUDA C using only Python. However, not every feature of CUDA C is supported, so if you know C and CUDA, your best bet will still probably be PyCuda. So first, we'll go briefly over Cupy. As I said before, Cupy is more or less a drop-in replacement for NumPy, but instead of performing the calculations on the CPU, you do them on the GPU. We'll look at an example in a notebook briefly. However, to use Cupy, there are a few things you should be aware of. The main concept you need to understand is the distinction between the host and the device. The host is effectively the CPU and the RAM. The device is your GPU. Usually these components are very much separated in your computer, and you mostly interact with the CPU and RAM. To run calculations on the device, the host must send the appropriate data and instructions to the device. The device has its own onboard RAM to store this data and these instructions. The device performs a calculation and sends the results back to the host. There are two important things to note here. First is that the RAM on the GPU and the RAM accessible by the CPU are very much separated. Data must be copied to this GPU memory for it to be able to work on it, and it must be sent back to operate on the results further with the CPU. These transfers are quite explicit, and also with Cupy, you must always be aware of whether you are dealing with data on the host or on the device. Secondly, these data transfers take time, and for simple computations, these can actually be the time-limiting step. Therefore, it's good practice to minimize unnecessary data copies and perform all necessary computations on the GPU before sending it back. Now let's look at a notebook to illustrate these concepts with Cupy. To experiment with Cupy and Numba, we'll work in this Google Colab Jupyter Notebook environment. You'll notice that if I try to import Cupy, it'll throw an error because module is not found. That's because we really need to have a GPU available for Cupy to work, obviously. So to do that, we go into runtime, change runtime type, and for the hardware accelerator, select GPU. It'll look like allocating, connecting, initializing, and once we're connected, we will be able to import Cupy as CP. And now we can work with Cupy. We'll also be importing NumPy to illustrate the differences between CPU and GPU. So first, let's create an array on the main memory on the host memory. And and we'll say random values between 0 and 255 with a size of, let's say, 2000 by 2000. We can view the array. It's just to illustrate a bunch of random numbers, and it's a matrix of size 2000 by 2000. Now you'll notice we can check how big this matrix is in terms of memory size. This thing is, well, to make it a little bit easier, 32 megabytes it takes in memory. To send this array to the GPU, what we have to do is say array GPU is equal to CP. So now we need Cupy as array CPU. And that will take care of sending this information or copying this information onto the GPU memory. We can actually view the data that is in here, and it'll be the same as was in the array of on the CPU. Now this is, to get this view, we actually have to get back the information from the GPU memory. Now this thing, sending of data, actually takes time, right? We can time how long it takes with the magic function timeIt. If we do cp.asArray CPU, it'll take a little bit of time to run this a couple times to see how long it takes, and this takes 5 milliseconds. If we make this array larger, let's say, 4 times as large, then if we time this, it's going to take much longer. So the more data you have to send to the GPU, obviously the more time it's going to take. If we check what the type is of our array GPU, we'll see that it is indeed a Cupy array. Now let's do a little operation on the Cupy and NumPy arrays. For simplicity, let's take a Fourier transform. So for the NumPy array, we will import from SciPy FFT. And let's time how long it takes to take a Fourier transform of the array on the CPU. So now we have this rather large array, 4000 by 4000. Okay, it takes about a little bit less than 400 milliseconds. To do the same thing on the GPU array, actually we cannot use this same function. So if you try fft.fftn array GPU, that's going to throw an error because this data is not available on the main memory. It's not a NumPy array. SciPy doesn't know what to do with this Cupy array. But we can take FFTs of our Cupy arrays from importing the GPU implementation of FFT. This can be found in from cupyx.scipy import FFT as FFT GPU. And this will behave exactly the same, more or less, as the SciPy implementation for the CPU. So if we do here, timeIt FFT GPU dot FFTN array GPU, this takes about 64 microseconds. So this is really orders of magnitude faster than the CPU implementation. Now notice here what it says. The slowest run took about 24,000 times longer than the fastest. So the reason is because these functions are actually underneath the hood CUDA kernels that have to be compiled when you call them the first time. Then after they are compiled, you cache them and it runs fast. But this compilation takes some time. So the first time you call a Cupy function, you will experience that it's oftentimes rather slow. And that is because it has to compile the kernel for it to work. To get data back from the GPU to the CPU, we have to use the function cp.asNumPy. And so let's send back the FFT of our array on the GPU. Let's say this is FFT sent back. And then we will also calculate this one more time. FFT CPU is FFT.FFTN array CPU. And then we can check whether these are similar. Oh, actually, we made a mistake here. The array on the GPU is still the 2000 by 2000, so we can fix that. Array CPU here, then array GPU, we send the data. And you can see that both arrays are the same. So the main thing to keep in mind with Cupy is to remember where your data is. Is it on the host memory or on the device memory? If it's on the host memory, then you should use the regular SciPy functions. Otherwise, if it's on the device, you should use the Cupy implementation of these functions. Using the FFT GPU implementation on the CPU array will not work. It'll throw an error because it's not a Cupy array. And similarly, FFT, as we already showed, that FFTN on the array GPU will also not work. So this is the most important thing about Cupy and pretty much all there is to it. Now there is one small caveat, and that is that some NumPy functions will work on Cupy arrays. So for example, mp.max array GPU, this will actually return a value. And you see that it's actually some array. So if we check the type of this, it will still be a Cupy array of dimension 1. So using the NumPy functions on a Cupy array, Cupy is smart enough to figure out that it must keep the data and operate on the GPU instead of on the CPU. If you want to copy the data back, either way, from the host to the device or from the device to the host, you have to do this explicitly because these operations take quite a bit of time. And one last thing to remember is that sometimes, if you have data that comes from a file, of course you have to send it from the host to the device. But if you're creating an array, it's better to create it directly on the GPU. So for example, instead of sending this random array to the GPU, it would be better to just use cp.random.randint 0 to 55 size equals 4000. And this will take a little bit of time because it must compile, but here you see that it did the same thing. Oh, actually, we made this a little bit too big, but there you go. Another random array, and this will actually be faster than creating the array on the host and sending it to the device. To summarize, Cupy behaves in many ways like NumPy. there are a few caveats that you can find described in the documentation. Important things to stay aware of is first is whether you have the data on the host or on the device. And related to that is if you want to use SciPy functionality on the Cupy arrays, you can't actually use SciPy. You need to use the implementations inside Cupy. The downside of Cupy, same as with NumPy and SciPy, is that you're basically stuck if you require a custom algorithm. NumPy and Cupy have a bunch of functions implemented in C, which are fast and work on vectors or multidimensional arrays. But if you need to loop over the elements in that array for some custom algorithm, you're out of luck, because that requires the Python interpreter, which is slow. In this case, often people resort to writing performance-critical parts of their code in C, C++, Python, or even Fortran. But actually, you can stick with Python using the just-in-time compiler Numba. We won't discuss too much about the details of Numba, but we will take a look at using Numba for writing custom CUDA kernels in Python. So this basically means if whatever you want to do requires loops and cannot be done efficiently with Cupy, you can look into the Numba option. This section will be a bit more theoretical, but I hope it gives you a basic understanding of parallel programming so you can go out and create your own algorithms. So we've been talking about CUDA kernels, but what actually is a kernel? Well, there is an analogy with a cob of corn that is composed of a number of kernels. A kernel is one element, similar to thousands of other ones, that make up the whole. In the case of a CUDA program, we divide the problem into a grid of threads, and a kernel is the program that will be executed on each one of these threads independently. This is actually very different from how we create a CPU program, as there we have to explicitate every operation, looping over arrays, creating new CPU threads, etc. With CUDA, the basic model of the problem is a grid, and a kernel must be able to run on each of these threads in the grid independently. A grid and threads are of course somewhat abstract concepts, so let's look at an example. Let's say we have a matrix A where we want to add 1 to each of the elements. In a serial implementation for the CPU, we would loop through all the rows and columns of the matrix and increment each element by 1. So how would this look implemented as a GPU kernel? Well, in the simplest case, we create a grid of threads that is approximately the same size as the array A. I will show you later how we can launch such a grid with Numba. But for now, just assume that this is how we define the problem. The idea here is that there is one thread responsible for each element of A. But you will often find that the grid cannot be exactly the same shape as the input or output array. So some threads should do basically nothing. Okay, so now we have to write a program that will be executed by each thread independently. How does the thread know what to do and which element of A to operate on? Well, this is how we could define a CUDA kernel with Numba that could do what we want. Basically, it's just a Python function that has the CUDA.jit decorator above it. The kernel takes one input, being the input array. The first thing we do in the kernel is to get the thread index via the special function CUDA.grid. In this way, each thread can know its own location in the grid. We can then use the location of the thread to index into the array A and increment the value by 1. But there's two important things to note here. First, we have to check that the indices of the threads don't try to access elements that are not actually existing in A. So if we don't check that the indices of the thread are smaller than the dimensions of A, we will access forbidden memory, which can result in all kinds of issues. So this is a very important part of the kernel. Always check that you're accessing valid memory. The second thing to note is that CUDA kernels don't and can't return anything. In this case, we are updating the information in the matrix A in place. The original values of A are overwritten. If we want to get out a different result, or if we don't want to overwrite the original elements, we have to copy the results into another array, which we would have to pass in as an argument. So this is really the basic idea behind kernels. It's a program that's executed simultaneously on all threads in the grid, and you can typically control what the thread does via its own location in the grid. Typically, you want the thread to operate on a single element of an array, but it's also possible for a thread to deal with multiple elements. You just have to be clever with how you define the grid and the kernel. Unfortunately, there is one additional layer of complexity. The story is a bit more complicated as we don't just have threads inside a grid. There is actually an additional hierarchical layer called the block. Threads are actually organized in a block, and it is these blocks that make up the grid. Each block has a coordinate, and each thread inside the block can know the block it is in via the CUDA.blockIDX properties. A thread can also find out the block size via CUDA.blockdim, but luckily all blocks in the grid are the same size, so all the threads should get the same value here. Thread coordinates can be defined relative to the block it is in, and this coordinates can be obtained via CUDA.threadIDX. All the values you see written in the threads here are block relative thread coordinates. Of course, sometimes one wants to know the absolute coordinates of a thread in the grid. You can do this manually with some math using the block ID, block dimension, and thread IDX, but you can just use the shorthand notation CUDA.grid as we went over before. Just to illustrate, if we take this thread in block 1, 1 and calculate the absolute coordinates, you'll see we get 6, 7, and you can count on the grid to see that this is correct. Okay, but why is it organized like this? Why are these blocks? Well, as it turns out, in addition to the big global memory that we have on the graphics card, there are small caches for each block. So all threads in a block share a bit of shared memory only accessible to the block. The advantage of this shared memory is that it is much faster to access than global memory. So in some algorithms, you can take advantage of this. Note also that each thread has a tiny bit of memory, so-called local memory, to keep track of small variables inside the thread. So the execution hierarchy really reflects the memory layout. To illustrate these ideas, we will look at the classic example of matrix multiplication. Suppose we have matrices A and B, which we want to multiply together. To get the first element of C, we have to multiply the elements of the first row in A with the elements of the first column in B and add them together. So let's write a little CUDA kernel for this. For this problem, it helps if we visualize the problem in this way. Suppose we define a grid that is the same shape of the output array C. Then we would define a simple kernel in the following way. You can see that we first find the location of the thread, check if the thread location is a valid element in C, then we define a small temporary variable temp for each thread. Then we loop over the elements in the appropriate row of A and the appropriate column of B, multiply them together and add them to temp. At the end, we set the appropriate element in C to the temp variable. To illustrate this for one element, suppose we take this thread at location 1, 2. Then what this thread will see is the following. We get our thread coordinates, these are in a valid range. Then we multiply all the elements of row 1 in A with the elements in the second column of B and sum. Then we set C1, 2 to this sum and we are done. And this happens concurrently in all the different threads at the same time. So all the values in C are calculated simultaneously. Remember that the temp variable is stored in the local memory for each of the threads. There is one issue with this rather naive implementation, which is that each thread will have to load the row and columns independently from global memory. For this case, it means that we have to load each row and each column 4 times, once for each time we need that row or column. There's actually a slightly improved way in which we can multiply matrices, which makes use of the shared memory. To understand the shared memory approach, which is quite a bit more involved, it helps to reintroduce our blocks. Suppose we have blocks of 2 by 2 threads in this case. Then let's define 2 shared memory arrays using CUDA.shared.array of a size that matches the blocks, as you see here in the beginning of the kernel. While this is seen by all threads in the block, the array gets created only once and is accessible by all threads in the block. The rest of the beginning of this kernel should start to look familiar. we just query some information that helps us locate the thread and check the shape of the grid. CUDA.gridDim will tell us how many blocks we have, so in this case 2 by 2. Then there's also the part to check whether our thread maps to a valid element in C. Note that I've drawn only two arrays SA and SB, but really each of these blocks has its own SA and SB arrays. In the first part of the algorithm, we will load parts of A and B into these arrays that are defined in the shared memory using this bit of code. We do this in a loop, loading the relevant tiles of A and B into memory that are required by the block. Here, TPB is the number of threads per block, in this case 2. Note that this implementation will only work for square grids and square matrices, but it can be easily adapted for non-square matrices. For the first block, for the first iteration of the loop, this will look like this. Each thread in the block is responsible for copying one element of A and one element of B into the shared memory arrays. To get the correct values, we abuse the fact that our threads have an absolute index x and y, but also an index relative to the block, tx and ty. Note that the similar thing is happening in all of the blocks. You just have to follow the indices. In the second iteration of the loop, we would load these pieces of A and B into shared memory. It might be difficult to follow here, so it may help to pause the video and check the indices yourself. Of course, just loading arrays into shared memory isn't going to do very much. We actually have to multiply some numbers. Well, we can actually just multiply these tiles together like a matrix product, as we did before in the simple kernel. If we do this for both iterations in the loop and add together the result, we will get the same result as if we had multiplied full columns and rows together. If you don't believe me, you can pause the video and do the calculation yourself on paper. At the end, each thread will have some temp variable which can be used to set the correct element in C. So if we put everything together, the kernel should look like this. We define our shared arrays for each block. Then in a loop, we load different bits of A and B into these shared arrays. We loop over the elements in the shared arrays to update the temp variable for each element, and at the end, we set our value in C. It looks reasonable, but this is actually an incorrect implementation. Remember that each thread is executing this kernel independently, so different threads might be at different stages in the kernel at different times. That means we could get a scenario like this on the right. The kernels on the right of the first block might be on the second iteration of the outer loop, while the kernels on the left might be on the first iteration. This means that the shared arrays can take all kinds of values at any point in time, so the product calculated in the inner loop is basically undefined. It will depend on the relative speeds of the threads. To fix this problem, we have to ensure that the threads stop and synchronize at two different points. First, after loading the data into shared memory, and then after calculating the product. If these thread synchronizations are not performed, one runs the risk of simultaneously modifying the shared array with one thread while another thread is still using it for the multiplication, giving an incorrect result. To think about all these things from the point of view of each thread is the challenge and the fun of GPU programming. So how much have we actually improved the matrix multiplication algorithm? Well, in this case, the elements in this tile will only be loaded from global memory into shared memory twice, once for each of these blocks. So instead of loading each element for the matrices A and B 4 times, we load them twice, a factor of 2 improvement. If we would make our blocks larger, we improve even more. But remember that shared memory is limited, so typically you will have to work with some type of tiling scheme. So let's now briefly look how to implement these things and call these kernels in a Jupyter Notebook. So here we're back in our Jupyter Notebook environment, and let's look now at Numba.cuda. So to use it, from Numba, import CUDA. And one of the cool things that you can do is you can actually check some information about your GPUs. with CUDA.detect. And you see here that actually the GPU we're using here is a Tesla T4. And you can check on the internet what the compute capabilities and hardware specs of this device are. Now, Numba.cuda has its own implementation of arrays. So if we again define an array on the CPU with NumPy, then we can use Numba.cuda to send the data over. With the CUDA.toDevice function. And now this information in this array has been copied to the GPU. Now this is actually very similar and interoperates well with Cupy. So actually we can do cp.asArray and since this array was already existing on the GPU memory, this will actually be rather fast because a Cupy array is just kind of a wrapper around array data on the GPU. To get the data back using Numba.cuda, we can do darray.copy to host. And that will send it back as a NumPy array. Again, very explicit, slightly different APIs from Cupy, but again, you can totally avoid using this copy to host and to device. You can always just use Cupy arrays if you want. Numba will work perfectly fine on Cupy arrays. So let's now define our matrix multiplication kernels. Sorry for the change of scenery and the change in audio quality, but I had to re-record this section and had to make do with the technology that I had available. So I've gone ahead and already filled out the code for the matrix multiplication kernels. We are first going to import Numba and Cupy. Then here, this is how we define our naive implementation of the matrix multiplication kernel as we saw earlier. Then we're going to create two random arrays, A and B, which will have element values between 0 and 10, and they'll be of size 2000 by 2000. We'll also create an array of zeros, which will be C, also 2000 by 2000, which will store our output. Now, we could just define cp.empty, but I'm using zeros here to illustrate the difference between the values. Just so you will believe me that the kernel works. So now we have created our arrays, and you can see that the array C is completely empty. Now we will have to define how we want to execute our kernel. So what we need to provide to our kernel execution method is the size of the blocks, or the threads per block, and the size of the grid, measured in how many blocks we have in the grid. So usually a good starting value for the number of threads in a block would be 128 to 512. And so a 16 by 16, that will come out to a value somewhere in between here. And so that will be decent when you're dealing with 2D arrays. Now the number of blocks in the grid will of course depend on the size of our problem. So what we typically do is we take the shape of the output array, we divide it by the threads in a block, and we round up so that just to be sure that we will have a thread for each element in the output array. So in the case of 2000 by 2000, let's see what we get. We will have 125 by 125 blocks in the grid. And the size of the grid will be exactly 2000 because 2000 is divisible by 16. Now, if we were to choose another size array here, then it might not be the case that the grid and the arrays match up exactly. To execute our kernels, our CUDA kernels, we use this type of notation. So we type the name of the kernel, then inside brackets we would provide the number of blocks per grid, so the size of the grid measured in blocks, and the number of threads in a block, or the size of each block. And then after that we would provide the arguments. So if we execute this cell, you will see that now C is properly occupied. And the same thing we can do for our fast matrix multiplication kernel. We won't go through the entire algorithm, but it's just copied from what I discussed before. So again, we define two arrays that we want to multiply together, and we'll use a size of 4000 by 4000, and we will define two output arrays, C slow and C fast, where we will store the output of the slow kernel and the improved kernel. Let's run that. Again, we would have to find out what our block size and our grid size is. So we calculate that based on this size over here. And then, just to be sure, let's run our slow kernel once more. And in the same way, we would run our fast kernel. And just to see, you will see that both kernels give the same result. So now let's time our kernels. Let's just run it 10 times. We'll first run the slow one, and it takes 14.5 milliseconds. How long is it going to take here? Very, very slightly faster. Actually, you won't really notice much of a difference because this implementation, it may still not be the optimal one. A better implementation is probably available inside Cupy itself. So if you would do cp dot, and we would do a b, then that should return the same thing as the kernels. Yeah, so that gives us the same result. And we can time this. And you'll see that this is actually probably the fastest implementation. So for simple things like matrix multiplication, you'll probably be best off with the built-in functions in Cupy. But if Cupy doesn't have what you want, and you really need to write your custom kernel, then if you're not such a C++ whiz, you might be better off with Numba.cuda. For working with CUDA, you will of course need an NVIDIA graphics card that is CUDA enabled. You need to have the right NVIDIA drivers installed, and you will also need the CUDA toolkit. The drivers and toolkit are unfortunately closed source, proprietary pieces of software. If you have ethical qualms about using proprietary software, or you don't have an NVIDIA GPU, the main alternative available to you is OpenCL. Similar concepts concerning the parallel execution of code apply, but there are no easy-to-use Python bindings at the time of making this video. The fact remains that CUDA-enabled NVIDIA GPUs remain king when accelerated computing is concerned, but let's hope that this may change in the future. So I hope this video gave you a good introduction to how you can leverage your GPU using only Python code, and going a bit deeper than off-the-shelf neural network libraries. If you're happy with what the NumPy API offers, you should go with Cupy. If you need to write something custom, go with Numba. In any case, both of these tools nicely interoperate, so you can always use both of them in the same project. Thanks for watching this video, and see you in the next one.